Hello viewers, welcome to Option Trading ki Duniya. In this episode, let me focus on probability theory. So these are a series of lessons wherein I am going to teach you the probability theory, which is very useful for stock market knowledge. For those who are new to opening trading and demat accounts. Hello viewers, welcome to Option Trading ki Duniya. In this episode, let me focus on probability theory. Probability theory is very essential for stock market trading. For those who are new to trading account and demat account, I request the viewers to open their accounts in Upstock, a leading stockbroker and a trustworthy broker with state-of-the-art trading terminals. Now, first let me come to the probability theory. Before I proceed with my presentation, let me tell my viewers that this content is for educational purpose only. So now, what is probability theory? So the probability phenomena is divided into deterministic and non-deterministic model. So what is this deterministic model? What is this non-deterministic model? So in the deterministic model, there exists a mathematical model that allows perfect prediction of the phenomenon's outcome. So a person is to predict perfectly the outcome. So you can find many examples in physics, chemistry, mostly in the exact sciences, in engineering, etc. Second one is a non-deterministic phenomenon. No mathematical model exists that allows perfect prediction of the phenomenon's outcome. Usually in social sciences you'll find this phenomenon. So non-deterministic phenomena may be divided into two groups. When we are speaking about non-deterministic phenomena, firstly we have got random phenomena. We are unable to predict the outcome, but in the long term, the outcome exhibits statistical regularity. I'll explain to you this one in detail. Secondly, there is haphazard phenomena, which means unpredictable outcomes. But in the long run, the exhibition of statistical regularity in the outcomes is certainly there in both random phenomena as well as the haphazard phenomena. So we have got deterministic, non-deterministic. In the non-deterministic, we have got haphazard phenomena and random phenomena. Now let me come to the haphazard phenomena. Unpredictable outcome, but no long run exhibition of statistical regularity in the outcomes. Do such phenomena exist? So there is a question before each one of you. Do such phenomena exist? Will any non-deterministic phenomena exhibit long run statistical regular eventuality? Will any non-deterministic phenomena exhibit long run statistical regularity eventually? These two questions are for you to imagine and think. Now firstly, let me bring out some of the examples. Unable to predict the outcome, but in the long run, the outcomes exhibit statistical regularity. For example, tossing a coin. When you toss a coin, outcome is head or tail. But you are unable to predict on each toss whether it is head or tail. But majority of the people say in the long run, 50% of the time heads will occur, 50% of the time tail will occur. But when you are tossing a coin, outcome is uncertain. So that is the meaning of random phenomena. Any head or any tail can come randomly. So proceed further. So when you roll a dice, number 1, 2, 3, 4, 5, 6, any number can come on the top. So we are unable to predict the outcome. But in the long run, one can determine that outcome is 1 divided by 6. Okay, but before that, the assumption is the dice should be balanced. One side should not occur more frequently. Yeah, there should be a symmetry in the dice. So all these assumptions are valid when you are throwing a dice. So now let me come to some of the definitions. The sample space for a random phenomena is a set of all possible outcomes. Very important, sample space, yes, for a random phenomena is a set of all possible outcomes. Now firstly, tossing a coin, what are the set of all outcomes? Head and tail. Rolling a dice or rolling a die, what are the outcomes? 1, 2, 3, 4, 5, 6. Yeah, next. What is an event? An event E is any subset of a sample space. Any set of outcomes, not necessarily all outcomes of the random phenomena. So you can see sample space is already marked. So this is sample space. And in that E is an event. So this circle is a subset. So circle is the subset. Now let me proceed further. So most of the probabilitical events are marked in Venn diagrams. So as you go further, you will come to know. Yeah, next. Let me focus on an event E is said to have occurred if after the outcome has been observed, the outcome lies in E. Now, very important thing is to note that there is a sample space and event has occurred. That outcome should be in the sample space. The outcome has been observed that lies in E. So that is a very important point to be noted. Now for example, rolling a die, outcomes 1 to 6. The event that, see there is an event. So yes, 1 to 6 is the sample space. The event that even number is rolled. There are 3 possibilities, 2, 4 and 6. So that event is part of the subspace. So therefore we call it as a subset. Now, what is a special event? Sometimes we call null event, empty event. Yeah, we mark with phi. So this is phi. So phi, the event that contains no outcome. Okay, the event that contains no outcome. The entire event is the sample space. Yes. The event that contains all outcomes is sample space. Yes. The empty event will never occur. There cannot be event without anything. So empty event will not occur. The entire event always occurs. There are when rolling a dice 6 possibilities. The entire event always occurs. Okay, now set operations on events. So firstly, let me concentrate on union. Let A and B be 2 events. Then the union of A and B is an event denoted by A union B. Meaning is any E, for example, any E, that E belongs to A or E belongs to B. So when you are going for union of A and B is the event denoted by A union B, which means that any E you take, E belongs to A or E belongs to B, one of them. So that is the union. Next, let me come to the okay. So let me proceed further. the event A union B occurs if the event A occurs or the event B occurs. Okay, so you just skip this and. So event A union B occurs if the event A occurs or the event B occurs. Both cannot happen at the same time. So A union B, for example, we have 1, 2, 3, 4, we have 5, 6, 7, 8 is there. So what is A union B? A union B is equal to, we have 1, 2, 3, 4, 5, 6, 7 as well as 8. Okay, A union B. Yeah, so now let us move further. Let us move further. Okay, intersection. So intersection is, let A and B two events, then the intersection of A and B is the event. So we denote it as A intersection B. Yeah, intersection. So this is the symbol. So which means E belongs to A as well as E belongs to B. So that is that, which means the common element from A and B is called as A intersection B. So very easy to remember. So we'll proceed to the next one. Yeah. So after learning union, intersection, let us come to complement. Let A be any event. So there is one event A. For example, when you are rolling a dice, even number comes on the top. Yeah, 1, 3 and 5. So A is an event 1, 3 and 5. Then the complement of A is defined by, complement of A. We write it as A complement, A dash. E does not belong to A. If suppose when rolling a dice, I give example 1, 3 and 5. So A complement is nothing but, so A complement if I write for, so other than 1, so 2, 4, 6 will be A complement, which means E does not belong to A. So 1, 3, 5 are the three numbers which belong to A. So remaining are A complement. Okay. So in many of the problems, you will recognize that you are working with union, intersection and the complement. So you have to always remember when we say union, this or that. Intersection, A and B. And is very important when it comes to intersection. Complement, not. Yeah, so next, if we proceed further, now we are coming to very important concept, mutually exclusive. Two events A and B are called mutually exclusive if A intersection B is phi. Phi means nothing. So null set. Now A intersection B is null set means no element of E belongs to B, no element of B belongs to A. So there are no common elements. In such a case, we call the two events are mutually exclusive. Now, if two events are mutually exclusive, then there are no outcomes in common. So both are separate. At the same time, they cannot occur. Yeah, because the outcomes are different. At the same time, they cannot occur. The outcome of random experiment cannot belong to both A and B. The outcome cannot be the same. Now, after learning these very important concepts, let us come to probability. So first let me define probability. Probability of any event. Sample space is defined there. Sample space, yes. The elements are O1, O2, O3, so on up to N. Finite number of finite number of possibilities are there. So n, finite number of outcomes. Also, each of the outcomes is equally likely. So equally likely means any outcome from O1 to On is equally likely because of symmetry. Then what is the probability of any event? So probability we denote always P of E. So that is here is n of E. So what is the meaning of n of E? Number of outcomes, yeah, in event E. So divided by total number n of sample spaces, n of A, number of elements in A. So n of A is number of elements in A. So suppose if you are throwing a dice, probability is 1 divided by 6. 1 is the outcome in event. So 6 is total number of outcomes. Any of the 1 to 6 possibilities are there. Okay. Further, let us move. Okay, this is defined once again. Number of outcomes in E divided by total number of outcomes, which you already learned. Applies only to a special case when sample space of finite number. So you have to always keep in mind, sample space should have finite number. When you are throwing a dice, sample space has got only 6 numbers possible. Each outcome should be equiprobable, means symmetric. You have to always remember symmetric. Yeah, the likelihood of each outcome is cannot be ruled out. So symmetric. If this is not true, whatever definition you are applying above is not valid. Okay, so let us move further. Yeah, first let us start with rules of probability. Additive rule. Suppose if you have 2 events, how do you add them? So in case of mutually exclusive, yeah, P of A or B, probability of A or B is equal to, you have to add probability of A plus the probability of B. Since they are mutually exclusive means whatever belongs to A does not belong to B, whatever belongs to B does not belong to A. So therefore P of A or B, or is nothing but union. So P of A plus P of B. Yeah, and you have to always remember there is mutual exclusivity. A union B is a null set. Yeah, let us move further. Yeah, if 2 events A and B are mutually exclusive, they have no common outcome. They cannot occur at the same time. This we already have explained to you. Now, this just now we learnt. P A or B is P of A plus P of B. So this is the additive rule. Additive. Okay. Usually, in general, so in case when it's mutually exclusive, P of only this much. But when mutual exclusivity is not valid, P of A or B is equal to P of A plus P of B minus P of A intersection. So this is there. So this is in general. So you have to always remember. Logic. So you understand the logic why P of A is equal to P of A union B is equal to P of A plus P of B minus P of A intersection B. The logic is when you are doing A union B, yeah, when P of A is added to P of B, the outcome in the A intersection is counted twice. See, we will consider all the elements of A, we will consider all the elements of B, but what happens is that the elements, some elements are in A as well as some elements are in B. So they will be counted twice in order to in order to remove one count, since we are counted twice, one count, we subtract from P of A intersection B. So that is the logic. Yeah, it is explained with an example. Delhi and Mumbai are two cities competing for the World University Games. There are also many others. The organizers are narrowing the competition to the final five. So Delhi and Mumbai are there. The organizers are narrowing the competition to final five cities. Yeah, there is probability taken. 20% chance that Delhi will be amongst the final five. 35% chance that the Mumbai will be amongst the final five. 8% chance that Delhi and Mumbai will be amongst the final five. So finally question is asked, what is the probability that Delhi or Mumbai will be amongst the final five? What is the probability that Delhi or P of A union B? So P of A is Delhi, B is Mumbai. So you can easily work out using the formula. So let A is the event that Delhi amongst the final five. B is the event that Mumbai is among. Already given. Probability of A is 20%, probability of B is 35% given in the problem. And A intersection B, both common, so that is 8%. So easily you can put in the formula and calculate. You will get probability of 47%. 0.47, that is 47%. Now rule for complements. So P of probability of A complement is nothing but we said cat is in the well, the other side is the cat is not in the well. So probability of the complement is equal to 1 minus probability of the event. So complement we always say not A. A complement is not A. Not A is nothing but not from the event, what is outside. See, E does not belong to. So this is already explained to you. If A is one event, A complement is outside that particular event. The event A complement occurs, the event A does not occur. Now let us come to A complement and A are mutually exclusive. If A complement is outside, A is inside. Cat is in the well, cat is outside the well. So that is, if total is A complement, probability of A complement and probability of A, both together is sample space, outside and inside. So therefore both together is equal to 1. So that is explained here. Probability of A plus probability of A complement is equal to 1. So that is the sample space S. Now let us move to the very important concept, conditional probability. Yeah. So this is very important to understand for us to work out the problems. Frequently before observing the outcome of a random experiment, you are given information regarding the outcome. So if I explain to you, before observing the outcome of a random experiment, you are given information regarding the outcome. So how should this information be used in prediction of the outcome? Namely, how should probabilities be adjusted to take into account this information? Now, for example, two events are there. The previous event has already happened, okay, which will have some influence over the next event. Usually the information is given in the following form. You are told that the outcome belongs to the given event. You are told that a certain event has occurred. So now let us understand conditional probability in terms of numericals. You can see here. Suppose that we are interested in computing the probability of event A. So probability of event A. Yeah, we had been told, so event B outcome has already come. Then the conditional probability of A given B. So after the outcome in B, what is the conditional probability of A? So we write it as P A over B. So probability of A given B. So because event B has already occurred. E is nothing but the intersection of events A and B, common in A and B, divided by the given event, that is B. And you should observe that if probability of B is not equal to 0. See, probability of B, if it is a null set, then 0, then it is not possible. Now rationale. What is the rationale behind probability of A given B or conditional probability? If you are told that an event B has occurred, then the sample space is restricted to B. So we said that event B has already occurred. Then the sample space is restricted to B. The probability within B has to be normalized. This is achieved by dividing P of B. So we know that event B has occurred. Now sample space is restricted to event B. Event A can now only occur if the outcome is in the form of A intersection B. Hence the new probability of A is. So you can see here, probability of A given B is equal to probability of A intersection B divided by probability of B. So A and B are there. We know the common elements. Okay, divided by probability of B, because event B has already occurred. And usually it is restricted to event B. Yeah, this let us illustrate with an example. The Academy Awards is soon to be shown. So award ceremony is soon to be shown. For a specific married couple, the probability that the husband watches the show is 80%. The probability that his wife watches the show is 65%. While the probability that they both watch the show is 60%. Now if the husband is watching the show, what is the probability that his wife is also watching? Okay. So we have already, so probability B, that event has already happened. That husband is watching the show. Probability of B. Now A is the event. We are wanting to find out the probability of A's wife watching the show, given that the husband watches the show. Yeah, both husband and watching is 60%. Now wife watching the show is 65%. So now probability of A over B is equal to intersection, that is 60% divided by 80%. So 0.75. 75% is the probability of event wife watching the show, given that husband watches the show. Yeah. Let us move further. Independence. Two events A and B are called independent. If independent, very important. Yeah. So probability of A intersection B is probability of A into probability of B. Independent event. That means two events A and B do not depend on each other. Now note, probability of event B is not equal to 0. Very important, these conditions. Probability of A also is not equal to 0. Then probability of event A given B is equal to, we already discussed, probability of A intersection B divided by probability of B. So we already know from independent events that probability of A intersection B is equal to probability of A into probability of B. Yeah, divided by probability of B. So probability of B and probability of B will cancel. So we have probability of A. Okay, in case of independent events, one event is not dependent on the other. Probability of A over B is equal to probability of A. From the problem itself we can understand the occurrence of event B is independent, so they cannot have any influence. So therefore probability of A over B is equal to probability of A. So similarly probability of B over A is nothing but probability of B, because A does not have any influence over B since they are independent. Now, difference between independent events and mutually exclusive. Two mutually exclusive events are independent only in a special case. So what is the meaning of mutually exclusive? Mutually exclusive means A and B cannot occur simultaneously. And mutually exclusive events are highly dependent. If one event occurs, the other event does not occur. So one depends on the other. And two mutually exclusive events are independent only in one special case. That is, probability of A is 0, probability of B is 0. And there cannot be any intersection. So this is the case. Yeah. In case of, see, probability of A intersection B is probability of A into probability of B. So we already know P of A with respect to B. So probability of A intersection B divided by P of B. And we just now discussed in case of independent events, that is P of A over B is equal to P of A. Yeah. So now P of A over P of S. So it is the ratio of the probability of set A within the ratio of probability of the sample space. If you consider the sample space, all the events to a particular event. Yeah. Now next one is very important, the multiplicative rule. So additive rule we have learned, the multiplicative rule. Multiplication means probability of A intersection B is nothing but probability of A into probability of B given A, probability of B, probability of P, probability of B, probability of A given B. So in this case, probability of A should be equal to 0. In the second case, probability of B should not be equal to 0. Yeah. So that is the thing we have learned in the first part. So naturally, probability of A intersection B is probability of A into probability of B when they are independent. So this word is very important. Yeah, independent events. So dependent events, we have got probability of A into probability of, so in case of dependent events. Yeah, probability models for random phenomena. Sample space, you know already we have learned. So event E is a subset. So in the sample space, yes, event E is the subspace. So this you already learned the definition. So summary. So far we have learned the first part. Now additive rule. Yeah, whenever, see, in the additive rule, very important to note, we have probability of A or B is equal to probability of A plus probability of B minus. This is important. If there is no common element, then this formula holds. Rule of complements. Yeah, probability of any complement is probability of 1 minus probability of E. Conditional probability, probability of A over B is probability of A intersection B divided by probability of B. Suppose if it is B over A, probability of B intersection A divided by probability of A. This is intersection. Now, multiplicative rule we learned just now, probability of A intersection B. So this is both we have learned. This is when probability of A is not equal to 0, very important. Probability of B not equal to 0. Independent events means we have got both are independent, so therefore there is no question of conditional. Now let's go to counting techniques. Finite uniform probability space. Many examples fall into this category. So we said in our case of probability we have got finite number, dice 6 outcomes, tossing a coin 2 outcomes, all outcomes are equally likely. So this is how we calculate probability of event E. And N of A is number of elements in A. So we say N of E, number of outcomes, N of S, total number of outcomes. Now suppose we carry out to have sets A1, A2, A3 and that any pair are mutually exclusive. So mutually exclusive means A intersection A1 intersection A2 is equal to null set. No common elements in A1, A2, A3, A4, so on. So N of I, that is N of AI is the number of elements in A. Let A is all the union. Union means all the elements from A1 to AN. Number of elements, total number of elements. So that is explained here. So A1 has N1 elements, A2 has N2 elements, A3 has N3, A4 has N4. So when we have A1 union A2 union A3 union A4, we will get all the elements in this 4. So next rule is, suppose we carry out 2 operations in sequence. The number of ways the first operation can be performed. The number of ways the second operation can be performed when the first operation has been completed. Okay. So this is very important because when you have got 2 operations, the first operation we perform first. Then once the first one is over, then second operation we perform. Then total number is n equal to first one into n2. Okay. You see. So in the diagram you can see n1 first operation, n2 many are there. So n1 to n2 1 2 3 4 5, here 5, here 5, here 5, here 5, here 5. So linkage is so many, you can link both of them in many number of ways. So now let us come to some examples. We have a committee of 10 people. We choose from this committee a chairman and a vice chairman. How many ways? Okay. N1 is 10 people are there. 10 people are choosing. We choose from this committee a chairman and a vice chairman. So anyways, number of ways chairman can be chosen because 10 people are giving their choice. Number of ways the vice chairman can be chosen. Yes, the number of ways, how many ways can be done? N. Number of ways is N, that is equal to N1 into N2. Number of ways chairman can be chosen 10. Once chairman is chosen, second event, vice chairman 9. 9 into 10, 90. So 90 ways you can select chairman and vice chairman. Yeah. In blackjack you are dealt 2 cards. What is the probability that it will be dealt a 21? In blackjack you are dealt 2 cards. What is the probability that you will be dealt a 21? The number of ways the two cards can be selected from a deck of 52 is 52 into 51, 2652. So you are taking out 2 cards out of the 52. Yeah. So that is a 21 can occur. The first card is an ace and the second card is a face card or a 10. So face card is a 10 point. A 21 can occur if the first card is the ace and the second card is a face card or a 10. Or the first card is a face card or a 10 and the second card is the ace. Yeah, so number of such hands. Number of such hands. So Jack 4 into, there are 4 cards. So that is 16. So 16 into 4, so 128. Thus the probability of 21 is, the number of such hands is 128. We have already calculated. Divided by the number of ways 2 cards can be selected. So that is 2652. Yeah. A blackjack, you are dealt 2 cards. Okay. So let us move further. The multiplicative rule of counting. Suppose we carry out k operations in sequence. So this is the multiplicative rule of counting. If you carry out k operations in sequence, n1 with the number of ways first operation is performed. N number of ways ith operation is performed, that is ni. So number of ways k operations can be performed is n is equal to n1, you multiply into n2, so on, multiply into nk. So you can see. So n1 is your first operation. So n2, n2, n2. So multiplicative effect you can see. Now let us come to permutation. How many ways can you order n objects? Yeah, permutations. How many ways can you order n objects? Ordering n objects is equal to performing n operations. Choosing the first object in the sequence, n1 is equal to n. Choosing the second object, n to n minus 1. Choosing the kth object, n minus k plus 1. So here, choosing the nth object, that is equal to 1. So we have n is equal to n into n minus 1 into n minus k plus 1 into, so last 3, 2, 1. So this is nothing but n factorial. So ordering n objects is equivalent to performing n operations. So how many ways can you order n objects? In n factorial ways. How many ways can you order 4 objects? A, B, C, D? 4 factorial. Yeah, very easy. Here are the orders. Here the individual order of A, B, C, D is very, very important. Next, permutations. How many ways can you choose k objects from n objects in a specific order? So now here, choosing the first object is n. Choosing the second object n minus 1. Choosing the kth object is n minus k plus 1. Total number of ways this can be done is n into n minus 1 into n minus k plus 1. So that is equal to n factorial divided by n minus k factorial. Some people will write n factorial divided by n minus r factorial. So always you remember that 0 factorial is equal to 1. Okay, 0 factorial is equal to 1. And some people write n permutations. I am writing npr is equal to n factorial divided by n minus r factorial. Yeah, here it is k is written. Usually n minus r. So npn is equal to n factorial divided by down is n minus 1, n minus n, 0 factorial. So that is equal to n factorial. How many permutations of size 3 can be found in a group of 5 objects? A, B, C, D, E. Yeah, it's not a combination, it is a permutation. So 5 objects are there. So 5 P 3. So 5 factorial divided by 5 minus 3 factorial. So that is 2 factorial. Yeah, so 60. So all the arrangements are here. Here the order of the letters are also very, very important. So we have a committee of 10 people and we want to choose a chairperson, vice chairperson and a treasurer. So 10 people are there. You want a chairman, vice chairman and a treasurer. 3 persons from a committee of 10 in a specific order. So size 3, group of 10. So 10p3. So 10 people are there, you need 3 people. So permutations you can use. So answer you will get 720. So we have a committee of 10 people and we want to choose a chairman, vice chairman and a treasurer. Suppose that 6 members of the committee are male. Additional conditions. 4 are female. What is the probability that 3 executives selected are all male? Again you can see in the problem we want to select 3 persons from a committee of 10 in a specific order. So 10 is the total size. Permutations are 3 of 10. Total number of A is, so 10 PR is equal to 10 factorial divided by 10 minus 3 factorial. 720. So now in case of sample space is S, assume that all outcomes in sample are equally likely. All 3 executives are male. So 6 executives you are choosing, 6p3. So we'll have 120. So lastly, probability we are calculating n of E divided by total sample space. Sample space is 720. The probability of event E is 120. So 1 divided by 6. So if all the candidates are equally likely selected for any position on the executive, male executive probability is 1 divided by 6. Yeah. So here in the slide you can see combinations. So far we have learned the permutations. What is the difference between permutations and combinations? So when we are arranging, in case of permutations, if you are arranging them in different orders, is not okay. You have to take all such possibilities. Even if you are arranging A, B, C, A, C, B, C, A, B, so all are different. But in the case of combinations, they are not different. Any order you can arrange. So you can see in the A, B, C, yeah, somebody can write A, C, B, which is not there. So here are the combinations of size 3, 5 objects at a time. So we have 5 objects C3. In combinations, ordering is irrelevant. So order is irrelevant. In permutations, order is relevant. So that is very important to note. Yeah. In how many ways can you choose a combination of size K objects from n objects? So in case of combination, order is irrelevant. Yeah. size k is unknown, ordering of elements of the combination to form a, so n2 is equal to k factorial. So you can find out. So npk, yeah, so permutations npk is equal to n factorial divided by n minus k factorial. The same formula, so n1 is divided by npk, some people use npr, here k is used, npk divided by k factorial. So we have got n factorial divided by n minus k factorial into k factorial. So if you expand it, n into n minus 1, n minus 2, so on up to n minus k plus 1. So if you write the denominator, then k into k minus 1, k minus 2, so on up to 1. So denotation is NCR. So this is how you denote. So it is the number of ways of choosing k objects from n objects, and usually NCR is binomial coefficient. So lastly we come to the binomial theorem, because when you are going for theoretical distributions in the coming module, in our next lesson number 2, we will be learning some problems on probability. So we see in the binomial theorem, x plus y to the power n is equal to nc1, so nc0. So we have got x to the power 0, y to the power n. Okay. The coefficient, that is nc0, nc1, nc2, so on up to ncn. Other elements are common elements. So you can see, yeah. So this NCR can be, the coefficients can be remembered easily using a Pascal's triangle. The number of ways this can be done. So the term xk into yn minus k will arise when we select x from k of the factors of x to the x plus y to the power n. So this is the triangle and this is the coefficient. Suppose if you have only 3 elements, we have got 1, 2, 1. If you have got 4 elements, 1, 3, 3, 1. So this looks like a triangle. It is called as Pascal's triangle. You see the entries. So first row, second row, third row, fourth row up to kth row, nth row. Yeah. 2 edges in the Pascal triangle contain 1s. So Pascal's triangle, you see 2 edges. All the edges contain 1. The interior entries are the sum of the total nearest entries. So this entry 2 is sum of these 2. Yeah. So this entry is sum of these 2. So this sum is 20. So you can see, many people will find it difficult, x to the power y, x plus y to the power 1, power 2. So we are using the coefficients here. So see, 4, 6, 4, 5, 10, 10. So these coefficients are being used. So it's always better to use the Pascal's triangle to remember the binomial coefficients. So now let us summarize. So n of, so rule number 1, n of A1 intersection union A2 union A3 union so on is nothing but we are adding individual items. So they are mutually exclusive. There is no connection between one and the other. The number of ways 2 operations can be performed in sequence if the number of ways the first operation can be performed So you should get all the possibilities of outcome in the first operation. The number of ways, all the possibility in the second operation you should get. Number of ways, k operations also data you have to get. So ordering is very important in case of permutations and combinations. The number of ways you can order n objects. So that is n factorial. So permutations we already said, number of ways you can choose object n in a specific order. So order is very important. You can arrange the objects. Here arrangement is not very important. The trick of probability can be applied anywhere. Okay. Counting problems are not easy. The more practice, better the technique. Probability is very difficult to understand. So more the practice, better the technique you will have. Now application to Lotto. Here you choose 6 numbers from the integers 1, 2, 3 up to 49. 6 winning numbers are chosen together with the bonus number. So 6 numbers. So how many choices for the 6 winning numbers? So using combinations. Because winning number can be in any order, so specific order is not required. So that is 49 C6. So 49 factorial minus 6 factorial, 43 factorial. So you'll get 13,983. So in case of Lotto, you can have various different types of problems. No winning numbers. So many events were given. So no winning numbers. 1 winning number, 2 winning numbers, 2 plus bonus, 3 winning numbers. So you can calculate all this if you know the probability, the permutations and the combinations. No winning numbers means you are losing. All 6 numbers have to be chosen from the losing numbers. So 43 C6, 1 winning number. So you have to identify the loser and then 1 winning number. The probability is 60,96,000. Second one is 1 number is chosen from 6 winning numbers. Okay. So all this you can go on and go on with the combinations. You can calculate all of this in your So finally, number of the event happening and its probability is mentioned in this particular table. So there are 4 cards there. A poker hand consists of 5 cards chosen at random from 52. The total number of poker hands is 52, 5 selections. So 52. So selected is 5. So the previous problem is explained. Nothing hand means X, Y, Z, U, V. Not all in sequence. So these are the explanations from all the 10 problems that is listed. So this is the theory for you to understand. You can go through each problem very carefully and try to get the answers. So for a change, just let me explain to you one of the problems. Before I conclude, let me just explain at least one concept. So we have got 8. So 8, what is the problem? 4 of a kind. So 4 of a kind, other one is a different. Yeah, 4 of a kind, so 8. So this is the one we have to choose the value of x. Yeah, 30C1. So 13. Select the suits for x. Okay. So we'll discuss the problems in detail in our next presentation. So thank you for watching this episode. For those of you who are not subscribed to my channel, please subscribe, like and share. I'll be coming with more videos on probability and statistics as we proceed further. So have a very clear mind and try to understand the concept clearly. You will be able to work out the problems. So thank you.